Welcome to Cambridge IGCSE Physics, Lesson 40.1, Basic Circuit Symbols. Today we explore the standardized symbols used to represent electrical components in circuit diagrams. These symbols form the universal language of electrical engineering and physics, allowing scientists and engineers worldwide to communicate circuit designs clearly and accurately. Let's examine our learning objectives for today. By the end of this lesson, you'll be able to, first, draw and interpret circuit diagrams with cells and batteries, understanding the difference between these power sources. Second, include power supplies, switches, and resistors in diagrams using correct standardized symbols. Third, include lamps, motors, ammeters, and voltmeters correctly in circuit representations. These objectives align with Assessment Objective 1, which focuses on knowledge and understanding of scientific concepts and vocabulary. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, circuit symbols, which means standardized drawings representing electrical components. These symbols are internationally recognized and allow clear communication of circuit designs. Second, cell, which means a single unit producing electrical energy from chemical reactions. A typical cell produces about 1.5 volts. Third, battery, which means multiple cells connected together for higher voltage. Understanding these terms precisely is crucial for circuit analysis and design. Let's explore our first core concept, power sources. The fundamental principle states that power sources provide electrical energy to circuits by converting other forms of energy, typically chemical energy, into electrical energy. For a single cell, we draw one short line representing the negative terminal and one thick long line representing the positive terminal. The voltage is typically 1.5 volts for common cells. For a battery, we draw multiple alternating lines, showing several cells connected in series. A typical battery might produce 9 volts. The key point to remember is that the longer line always represents the positive terminal, regardless of whether it's a cell or battery. Now we examine control components. Switches control current flow in circuits by either allowing or preventing the flow of electrical charge. An open switch creates a gap that prevents current flow, like turning off a light. A closed switch provides a complete path that allows current to flow freely. Resistors oppose current flow and control the current magnitude in a circuit. The resistance unit is the ohm, symbol omega, named after German physicist Georg Ohm. Variable resistors allow adjustment of resistance values to control current precisely. Our third core concept covers output components that convert electrical energy into other useful forms. The lamp symbol is drawn as a circle with a cross inside representing the filament that glows when heated by electrical current. Lamps convert electrical energy into light energy and heat energy. The motor symbol is a circle with the letter M inside. Motors convert electrical energy into kinetic energy, producing rotational motion. Light-emitting diodes, or LEDs, are shown with an arrow symbol and convert electrical energy very efficiently into light energy with minimal heat production. Measuring instruments monitor electrical quantities in circuits. An ammeter measures current in amperes, the SI unit for electrical current. The ammeter symbol is a circle with the letter A inside. Crucially, ammeters must be connected in series with the component being measured, so all current flows through the ammeter. A voltmeter measures voltage in volts, the SI unit for electrical potential difference. The voltmeter symbol is a circle with the letter V inside. Voltmeters must be connected in parallel across the component being measured to measure the potential difference between 2 points. Let's analyze a complete circuit containing all major components. The circuit includes a 12-volt battery as the power source, a switch to control current flow, an ammeter to measure current, a 10-ohm resistor to limit current, and a lamp as the output device. A voltmeter measures voltage across the lamp. When the switch closes, current flows from the positive terminal of the battery, through the switch, through the ammeter which measures the current magnitude, through the resistor which limits the current, through the lamp which converts electrical energy to light and returns to the negative terminal. The voltmeter, connected in parallel, measures the potential difference across the lamp without affecting the main current flow. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks you to draw the symbol for a battery with 3 cells. Remember that each cell is represented by alternating short and long lines. Question 2 is intermediate level. Design a complete circuit containing a battery, switch, resistor, and ammeter. Consider the correct connections and current flow path. Question 3 is advanced level. Explain why voltmeters must be connected in parallel across components, not in series. Think about what happens to current flow and measurement accuracy. For all questions, draw symbols clearly, label all components with appropriate values, and check that connections make physical sense. Circuit symbols power our modern technological world. In electronics manufacturing, circuit boards are designed and manufactured using standardized symbols that ensure global compatibility and understanding. Automotive engineers use circuit symbols to design car electrical systems, from lighting to engine management. Architects and electrical engineers use circuit symbols in building plans to show lighting circuits, power distribution, and safety systems. These applications demonstrate why learning circuit symbols matters. Career opportunities include electrical engineering, electronics design, and renewable energy systems. The symbols we learn follow IEC standards, the International Electrotechnical Commission, ensuring global consistency in electrical communication. Let's review the solutions. For question 1, a battery with 3 cells requires 6 alternating lines. Short line for negative, long line for positive, repeated 3 times in sequence. This represents 3 cells connected in series. For question 2, the correct circuit connects battery to switch to ammeter to resistor, then back to battery, forming a complete series circuit where current flows through each component. For question 3, voltmeters connect in parallel because this arrangement measures potential difference across components without interrupting the main current flow. Series connection would stop current flow entirely. Exam success requires clear symbol drawing using rulers, proper component labeling with values, checking complete circuit paths, and carefully distinguishing between cells and batteries. Let's summarize today's lesson on basic circuit symbols. The key points to remember are, first, power sources include cells, which are single units producing about 1.5 volts, and batteries, which are multiple cells connected together for higher voltages. The symbol difference is crucial for circuit analysis. Second, control components include switches that control current flow by opening or closing the circuit path, and resistors that limit current magnitude measured in ohms. Third, measuring instruments have specific connection requirements. Ammeters connect in series to measure current flow, while voltmeters connect in parallel to measure potential difference. For further study, practice drawing circuit diagrams daily to build familiarity. Learn how each component functions and connects. The next lesson covers current and voltage relationships, building on today's symbol knowledge to analyze circuit behavior quantitatively.